It was morning in the universe and much colder than anyone had expected when light from the first stars began to tickle and excite their dark surroundings nearly 14 billion years ago. Astronomers using a small radio telescope in Australia reported on Wednesday that they had discerned effects of that first starlight on the universe when it was only 180 million years old. The observations take astronomers farther back into the mists of time than even the Hubble Space Telescope can see, and raised new questions about how well astronomers really know the early days of the cosmos, and about the nature of the mysterious so-called dark matter whose gravity sculpts the luminous galaxies. We have seen indirectly evidence of very early stars in the universe, stars that would have formed by the time the universe was only 180 million years old, said Judd Bowman of Arizona State, leader of the experiment known as EDGES, for Experiment to Detect Global EOR, in an email. Dr. Bowman and his colleagues published their results in Nature Wednesday. The presence of stars manifested itself as a telltale dip in the intensity of a bath of radio waves, so-called cosmic microwaves, left over from the fires of creation itself. The dip meant that cosmic energy was being absorbed by primordial clouds of hydrogen gas that hung over the universe like a fog, but whose atoms had been thrown out of balance by the sudden presence of starlight. The presence of the dip, at a characteristic wavelength of hydrogen, confirmed earlier predictions from models of how and when the stars were born. But the depth of the dip and the amount of the absorption was a surprise. It suggested that the gas inhabiting the cosmos was only half as hot as astronomers had calculated, only about 3 Kelvin above absolute zero, or -454 Fahrenheit. This is difficult to explain based on our current knowledge and assumptions about astrophysical processes in the early universe, Dr. Bowman said. One possibility, suggested by Renan Barkana of Tel Aviv University in Israel, is that the primordial hydrogen could have gotten chilled by interacting with the dark matter that also permeates the cosmos. If true, this would be the first clue about the properties of dark matter, beyond its gravitational pull, which is how its presence has been inferred, said Dr. Barkana, who published his idea in an accompanying paper in Nature. How this all played out was the result of a subtle dance of atomic physics and thermodynamics, the study of heat. In its early days before the stars lit up, the universe was a fog of hydrogen and helium that had been synthesized during the first 3 minutes of time and that was now basking in the fading heat of the Big Bang. Hydrogen in empty space is prone to radiate radio waves with a wavelength of 21 centimeters. At first the gas and the microwave were in tune with each other, and the hydrogen was emitting just as much as it received from the background radiation bath. But when the stars began to turn on, ultraviolet radiation from them altered the energy levels of the electrons in the hydrogen atoms, knocking them out of sync with the microwaves, decoupling them in the physics vernacular. Since the gas was already physically much colder than the radiation, it began to absorb the 21 centimeter waves from the cosmic background, creating a deficit, or a dip. The shock was how great a dip that was, and thus how much colder the hydrogen was than cosmologists had figured. Enter cold dark matter, the only known cosmic constituent that can be colder than the early cosmic gas is dark matter, Dr. Barkana wrote in his Nature paper. Astronomers know that dark matter makes up about a quarter of the universe by weight, way more than atomic matter from its gravitational effects on stars and galaxies. The leading explanation has been that it consists of clouds of subatomic particles left over from the Big Bang. They're called WIMPs, for weakly interacting massive particles, and are hundreds of times as massive as a hydrogen atom. Because these particles are so massive, they are also slow, or cold in cosmic jargon. In theory, they should be passing through our bodies and everything else by the millions every second. But over the last 3 decades, increasingly sensitive attempts to detect these particles directly have failed, and theorists are beginning to consider other more complicated models of what they call the dark sector. Now the EDGE's observations might have opened a new window into that dark realm. And any progress in identifying dark matter could revolutionize particle physics. The idea that dark matter could have cooled the primordial hydrogen would imply that dark matter particles are only a few times heavier than hydrogen atoms, well below the commonly predicted mass of weakly interacting massive particles. Dr. Barkana explained in his Nature paper. It would mean that radio astronomers have a way of getting a grip on dark matter. None of this is for certain yet. Both Dr. Bowman and Dr. Barkana emphasized that the observations need to be confirmed by other instruments and experiments. The EDGE's result was based on averaging observations over the whole sky. But new projects in the works, like the Square Kilometre Array in Australia and South Africa, will be able to measure these temperature discrepancies in different parts of the sky and track the different evolution of dark and luminous matter.